Hello and good morning, and it's September 23rd, another sunny day in a long run of just solid sunny days here. It's fantastic and cool. 22 degrees, fantastic. So, okay, this is day 2 for this radio. Day 1, one of the things I noticed was obviously these floppy capacitors. And boy, still wondering why whoever did this just left them like this. Like, why didn't he cut the wires shorter? In any case, the other thing I have noticed is very poor wires in here, especially these yellow ones. Anywhere you see a yellow wire, the insulation's cracking off. Like just now when I tugged on this, the black wire knocked some insulation right off this wire here. Now some of those, the insulation's only necessary where the wires contact each other. But having all the insulation coming off just really increases the odds of something kind of unfortunate happening. What's going on down in here? This red wire is another floating connection here with another capacitor right here. Okay, let's take a closer look at what was done, and we'll study the schematic. Ooh, I gotta find the schematic. Yeah, we should study the schematic at this point. The assumption here is whoever did the work was simply adding in more capacitance and paralleling it into the existing big tall capacitors here. One of them I noticed is disconnected entirely. I think it was this one down here. The other two original capacitors are still connected for reasons I would kind of wonder about, because if you're going to augment a 14 microfarad capacitor with a 14 well, just get rid of the original one. And it's not hard to do. You just have to nip the connector off the top. And you can leave all the connections there. So for some reason this fellow decided just to parallel in some new capacitors now. Obviously this one, maybe this orange one here too. These red ones, which I don't think are directly related, but they don't look original to me either. This one doesn't look particularly original either. It's up on long wires. It's kind of floppy. Let's start with the schematic. I'm going to hunt down a schematic for this radio, and then we're going to look at how these capacitors are done, these ones. And we'll take a look at these, what was done with them, and make a decision on what to do about them. I think it's going to be pretty simple in the end. But there's lots of room here for something to go wrong. Let's see if I can find the schematic for this radio. The owner of the radio has sent along a file with it, and we're looking at it now. This file is very large. You can see the slider over here. We're halfway through a booklet of many schematics and service information for many radios. So here we are, 512A, X, and Y. Let me just take a look at the nameplate here while you look at that. And this is a 512. There's no A, X, or Y here anywhere. Well, Now this is a Canadian-built radio. It may or may not be a special design or design specific to Canada only. Could be an American design that's been altered a bit, not even altered a bit. Notice they don't say Canadian Westinghouse here. But the model number is 512 with no extension letter, so you'd think, well, this must be the earliest version of a number of versions of this radio. And they may not be date oriented. It could be they came out with all 3 of these at once in different cabinets and things like that. So the first thing we need to do is look over, this is a different radio here, we need to look over the information. Note R2 was 1 meg on early production. There's little notes hidden in these manuals, and unfortunately I have a bad habit of not availing myself of all the potential information that can exist in these. So here we are. So it's a couple pages. General features. Let's take a minute and just read that. These receivers employ the same chassis and have many distinctive features. The mantle model employs an 8-inch dynamic speaker, and the console model employs a 12-inch. So we have the 8-inch here. Mantle model. The superheterodyne circuit is used with such features of design as magnetite core adjusted IF transformers. That sounds kind of ordinary to me. Air dielectric trimmers. Also sounds a little normal. Oral compensated volume control. So I think what they're talking about there is the volume control is set up in such a way that when the volume is low, the bass is boosted. Maybe the treble too, but mostly the bass gets boosted up. Because our hearing is not the same at high level and low level. We hear the spectrum, audio spectrum, differently at different volume levels. Continuously variable tone control. Well, these old radios often had a snap tone control with 2 or 3 discrete settings. It was a switch rather than a control like this one. Continuously variable tone control with music voice switch. Music voice switch automatic volume control. What are they talking about there? Music voice. It's music dash voice switch automatic volume control. Okay, I don't know what they're talking about. Resistance coupled audio system. Well, I guess what they're trying to say there is they avoided using transformer coupling in the audio circuits, and that's 100% normal in these radios. The audio transformers have problems with tone. All metal radiotron, so that answers the question about whether these came with metal tubes or not. This radio came with metal clad tubes. And a dust-proof speaker. Yeah, I was holding it yesterday, and the whole back of it is in a can, but not the cone part. The back of the cone part's exposed, so not completely dust-proof loudspeaker. Trimming adjustments are located at accessible points. Their number is reduced to the least that is consistent with efficient operation. Tuning is continuous throughout the 3 ranges. That last statement, wow, what, they just had to fill out that paragraph there, I guess. They came up with another 8 words to stick in. Okay, nothing terribly special there. Circuit arrangement, we should read through this too, I guess. The engineers offered this, so why don't we read it? The first detector and oscillator functions are accomplished in a single tube, the 6A8. Notice they call it a W6A8 because they want to sell the Westinghouse tubes. In case some fool thinks they have to buy a W-6A8. The input of this, I shouldn't knock them, they're trying to make money with these radios. The input of this tube is coupled to the antenna through a tuned transformer. The RF coil system is greatly simplified in comparison to previous years. The antenna coil consists of only 4 windings to cover 3 ranges. By referring to the schematic circuit diagram, it will be noted that by an extremely simple switching circuit coil, L1, my grammar didn't work there. By referring to the schematic circuit diagram, it will be noted that by an extremely simple switching circuit coil, L1 is used only as, I sound like one of those computer readers, is used only as the shortwave secondary coil. L2 is used, depending on switch position, as either shortwave primary or medium wave secondary winding. And this is why these coils and their attached switches just drive me bananas, because the engineers come up with clever ways to utilize these coils. And this is an interesting example where in one case the coil is a primary, and in another case it's used as a secondary. L3 is used either as the broadcast secondary winding or the medium wave primary winding. L4 is the broadcast primary winding only. Some engineer worked a long time to get this sorted out. just to reduce the number of coils in the radio and save 20 feet of wire. The oscillator coil system uses 3 separate windings in the grid circuit and 3 separate windings in the plate circuit. The unused lower frequency windings are shorted out by means of the shorting bars on the range selector switch. Okay, quick look through here, because sometimes there's just little things that we gotta know right away. 3 terminals shown, the layout of the parts, I think as viewed from above, no, from underneath, and all these voltages are given, which is very, very helpful. Here's a spot here, it says right here, connect cathode ray between this terminal and chassis. Cathode ray oscilloscope when doing alignment. Very good. 600 series trimmer on rear apron. Socket voltage, IF trimmer location. How about look at this note? Hey, look at this. These ones are written in ordinary print, but this one's written in bold, all caps here. What have they done? When aligning the RF circuits, the chassis bottom shield must be in place on the chassis and securely fastened with all of the retaining screws. If the chassis bottom plate is removed, coil shielding will be incomplete and the RF circuit will oscillate when adjusting IF cores with the chassis bottom plate removed, or during troubleshooting on the chassis. Oscillation may be prevented by using a short length of wire with 2 clips to connect together the partition shields between the antenna and detector coils and between the detector and oscillator coils. Do they show those shields on a diagram here? So what they're saying is, with this thing on the bench here with the bottom off, there's a good chance of oscillations occurring. So this is showing all the layout, but they didn't show the plates here. And why are there 2 schematic? So this is the layout of the parts and the wiring. That's very helpful stuff. This is the schematic diagram here. It does look kind of sparse for parts, but I think it's because they've drawn the parts very small compared to the size of the the paper here. So it looks like a whole pile of wires with not many parts in it. Well, when I operated the radio, I didn't notice anything funny happening. But it could be it's not tuned up to peak. Once everything is tuned up to peak performance, at that point oscillations may kick in. So maybe this is something I should be aware of and not worry too much about until I have to. Well, here's another note. This is for alignment. It's down the way, but let's read it. When adjusting the air dielectric RF trimmers, it is necessary to use a special tool to slacken the lock nut on the trimmer previous to the adjustment. Shouldn't that be prior to the adjustment? And to tighten it again after the adjustment. So, okay, well, you can do that with a pair of pliers. Another special tool is available for making the actual adjustment to the trimmer. So I have a tool I use for these trimmers. The adjustment should be made upward or downward on the plunger with a twisting motion. Thank you for explaining that, because the first time I encountered these kinds of capacitors, I didn't know what I was doing with them. The special tool designed by the Canadian Westinghouse company for this purpose is double-ended, one end having a pin for the RF adjustments, and the other end is the special socket screwdriver for use in making IF adjustments. Special socket screwdriver for use in making IF adjustments. Well, what's so special about those? Okay, and that's a schematic layout. So let's look back at the radio for a minute and digest some of this information, especially about these plates here. I was talking about these plates, and it said take a short clip lead and clip something to something, but why would that be necessary? These plates are bolted right into the chassis. Okay, so we'll look at the radio, and I will read that part once again. Let's see if we can understand this. Where's the sentence start? Oh my God, it's a mile-long sentence. If the chassis bottom plate is removed, coil shielding will be incomplete, and the RF circuit will oscillate. There's the period. When adjusting IF cores with the chassis bottom plate removed, or doing troubleshooting on the chassis, oscillation may be prevented by using a short length of wire with two clips to connect together the partition shields between the antenna and the detector coils, and between the detector and oscillator coils. So they're using the word detector there, and these old radios often, what we would call the mixer tube, they call the first detector. So not to be confused with what we typically call the detector tube, which is later in the circuit. So it's saying between the antenna coils, the look at this. There's screw holes here. So that bottom plate must screw in right here to tighten this up. So this radio must have a real problem with coils accidentally interacting with each other, and they've gone through quite a length to prevent that from happening. And even with the bottom off, it can start happening again. So if this coil is interacting, these coils can start to interact. They said antenna coil. I don't see, and they talked about 3 different coils there. Let me just read this again. Oscillate short length of wire to connect together the partition shields between the antenna and detector coils, and between the detector and oscillator coils. Between the antenna, let me see these two. Well, if we encounter oscillations, then we kind of be suspicious about where they're coming from. Where is an antenna coil? Isn't this an antenna coil? One of these would be the antenna coil, probably this one because of this big piece here. Okay, I'm not gonna worry about it, but at least made a note about it. Now let's look at the actual circuit and these connections. Let's look at the connections first. So this one is going from a chassis connection on the black wire, of course, and the red wire is just going where these red wires are behind this resistor here, right to the top of this first capacitor. No, that's a middle capacitor. This one is the negative, same thing, going down to the chassis, and the positive going to this connection, which probably looks like it was cut off the top of the original capacitor. Same thing I'm probably going to do to these others. You only cut one off, but not the others. And there's a wire there. Insulation coming off. Wire here with the insulation coming off. Wow, this is really a precarious thing. Very, very precarious. Okay, so I'm imagining now how I can put new capacitors in here nicely and neatly. What about this one? So this one's also connected to ground and to here, to the same place as this. So these two are in parallel. This one appears to be by itself. And now who's augmenting this capacitor up here? There would appear to be nothing, but it's hard to tell. There's a red wire over to here. I don't think this first one got any kind of augmentation. There's no additional capacitor for it. So how big is this? This was a 14. 450 volt, 14 micro. This is probably going to be the very same. 14 here, and then this guy. You can turn the cardboard shell here. Ooh, that looks like a big number. And the flashlight. 10. It's not a big number. 10 at 450. So it's got a 10 and a 14. So it's got 25 and 15 basically. Let's take a look at the schematic now and see what size these capacitors are. Well, they're right here. Oh, no, wait a minute. You can't see them. Hang on. They're right here, but the size isn't written here. So we'll look on the schematic. Here we are. Now let's zoom in a little bit. This is bound to be them here. So one of them is a 10. Another one is looks like 18. And now there's 3 of them. So where's the third one? Maybe bypass at the output tube. So we'll find the cathode of the output tube. It's right here. It just goes right to ground. Okay, so they're not using special symbols here to recognize the type of capacitor. They're all drawn the same way. So we need to look for another large capacitor in here. Could be on the shield line. So we'll find the shield line, the shield supply, right here, this line here. 0.1, that's not it. On this wire here. Goes into that long resistor on the back of the radio. Could draw this capacitor just about anywhere. No, it gets past this resistor. I don't see it. What's that? Does that say 10? That looks like 10 to me. 10 microfarads. Well, that's what it looks like. I don't know what else it could be. You can see the dot right there. Now, normally we would put a 0 past the decimal point these days, but not back then, I guess. So what's it doing over here? Great big capacitor. It's going to the chassis, so it's trying to bring a chassis. Well, it's an awfully large capacitor for sitting at the bottom of these coils. So maybe that's not it. I wonder if that's why he left the one. What he did was he went after these two in the power supply, and he left this one as is. Range selector switch shown in shortwave position. Aren't there 3 bands on this radio? So there are 3 bands. What do you mean shortwave? There's 2 shortwave bands. It's probably the higher frequency one. So here's a tone control. Oh, what about those controls? There were too many of them. So here's one with a potentiometer. Here's another one. This is the volume control here. Is there a third one in here somewhere? Well, we'll just look for a moment here. It's almost certainly in this part of the radio. This is ground on a shielded wire. If I were a volume control, where would I be hiding? I'd be in here somewhere. Well, I don't see it. So we'll leave that as another mystery. How come you've got 3 volume controls? Here's a switch. What would this be? I can't quite read what it says there. It's tied into this network of resistors and capacitors here. probably affecting the audio. Well, that's the volume control right there. Off the volume control. But there's no input on the back. Whoops, no input on the back of the radio for a phono. Don't know exactly what that is. I don't remember there being, here's the band switch. Well, that's pretty weird looking too. Look how they're showing it. Another part of the band switch. Another part of the band switch. See how these are selecting either this or this stuff. Okay, we could stare at this for quite a long time, trying to spot things. But as we go along, we'll be referring to it along the way, and maybe then I can pick up on some of these things I haven't quite spotted yet, like the mystery volume control, or whatever control it is. So getting back to the capacitors here, so we have a 10 and an 18, and he's augmented. Let's see, the one he cut away, he put 2 capacitors in to get up to around 18. He's got a 14 and a 10, so he got up to 24. The other one, he just put a 14 in right here. And then the last one, maybe this one, he just left. So for now, we should just clean this up. Cut away the other one here and put in some brand new capacitors. We'll just get rid of all the stuff he's got in there. And oops. We'll go from there. Good. Oh, okay. Coffee. It's coffee break time. Whoops. Time for a coffee break. Okay, so I have this replacement capacitor, a little tiny guy like that. 400 volts, 22 microfarads, going in to replace the, was it 18? 18? That would be this guy and this one. I'm just double checking now to make sure I've got this right. I think I do. So what I'm going to do is I'm going to leave some of this black wire here just in case it's useful. I doubt it will be, but I'm going to leave some. In the radio for now, we're going to nip this guy right off. And then we're going to take this one out also. And I'm going to do away with, cut it as close to the chassis. Now I can see the guy did soldering way down on the chassis here, which you can't quite see. Well, you can see a little bit down in there. Soldering down to the chassis is difficult because the chassis is a big piece of metal. It'll take away the heat so quick. You can't, a little soldering iron can't heat things up. I can't get there. So right near this coil, I do not want to damage it. Okay, cut something there. Yep, this capacitor. The mini cap. 10. Made in the USA. Well, I'm going to put a test on these, and I'm not sure what to make of the result that's going to come. I'm going to try it anyway. Whoops. And I'm going to use this modern tester here, as opposed to using the classic leak tester, because these are electrolytic. Now I don't know what to expect on this. Let's see what it does. Okay, it's saying it's a capacitor. So it says it's 23 microfarads, but in fact it's 14. So how come this thing reads it at 23 when it's really supposed to be 14? Now, how accurate are these? In the older days, they're not accurate at all. In fact, if you bought a 10, it was probably a 20. because they couldn't manufacture them consistently enough. That's really old. It's got some stuff coming out of it. Generally speaking, a higher reading on these devices than what it should be indicates there's excess leakage through the capacitor. And I would test this on my high voltage tester, except I have no experience, so I wouldn't know how to judge the result, because it's just a qualitative test. So that's that one. Let's try this one. We'll probably get the same result. This is supposed to be a 10. We'll probably measure it high. Which you might find reassuring, but I don't think it is. I don't think it's reassuring at all. Well, not much higher. 2.3 V loss. So I don't know how to interpret that stuff. ESR, that's a high number, 4.1 ohms. But again, I really don't know how to interpret that on these capacitors. Okay, let's try the brand new one. Yeah, there's an idea. How does it compare? Well, let's see how this comes out. Okay, so it says it's 18 microfarads. The ESR still shows a little high, but I don't know what that means. V loss, again, I'm not sure how to interpret that on these capacitors. 18, so 19 microfarads, according to this tester. It says 22 on it. I don't know. I'm sure it's fine. When I say I don't know. Electrolytic capacitors are not as simple as a regular capacitor because they have an inherent amount of leakage in them right from day one. It could be very, very small on day one, but still it's there. So we're going to want to put this way down in there. Let's take a close look at these connections so we know what we're dealing with, because there's cracked wires everywhere. And I could easily get into trouble here without even knowing it. So these are cloth covered wires mostly. Okay. So the insulation's come off that yellow wire there, but very close to the terminal. You see right next to it is a uninsulated wire, so you can't panic too much about wires being uncovered. It's exactly where they're uncovered. Oh, look at it down in there. Wow. See, if I start replacing these, that'll become a whole job in itself. What's that? That little fly right on the end of the... some kind of insect right there. That's his last spot. He landed there to take a break and never left. Couldn't find his way out of the radio. Okay, no more flies. So I want to get way down. See the schmozzle solder job there? Well, that isn't right to the chassis. That's to a... hold it. Everybody hold the fort. That capacitor looks like it's on an insulating plate. If you look right where the chassis meets the capacitor plate or whatever, it looks like there's some fibrous material in there, brownish fibrous material. When I looked on the top, see this one? This one is screwed down tight to the chassis. This one's got something going on. Now, from the top, they look like they're all... This one's got something going on, too. Not that it matters anymore. So a couple of these, two of these are not tied to the chassis. So it looks down below here. Let's take a look up above now. This doesn't matter much for the capacitor I'm putting in. Oh yeah, there's a little insulator in there. This is the tall... towers of capacitors here. So I missed that because when I look down from above, well, how could I miss that? Look at that. So I'm talking about the insulating pad that the capacitor is sitting on. So these two, these are the two lower ones, pretty clearly insulated from the chassis. This last one, I don't think so. We got to go back to the schematic and take a look at how this is done. But again, it won't matter because the capacitor I'm putting in, it doesn't have a metal shell to worry about. You just have to make sure this ground terminals, the negative terminals, in the right spot. That's all. But let's look at the schematic and just look at the grounding of these capacitors. This is something that's easily overlooked. So here we are here. So we would assume this part here. See, look, there's a resistor to the chassis. 225 ohms. So you can think this is probably that resistor at the back of the radio. Right down here, including this piece. This is probably the bottom. This is probably where that bug was, sitting right here. And what they've done is they've applied the chassis ground up on this voltage dividing resistor here. A result is this voltage here relative to this is negative. Right? More positive up here, less positive, less positive. So by applying the chassis ground here, and you can see all the different things that are grounded to the chassis in this radio, all kinds of stuff is grounded. That leaves this as a negative voltage that can be used for biasing. So let's chase this wire, probably 5 or 10 volts negative. Where's it going? It's going right up to the grid of the output tube, and that explains why there's no cathode resistor, which I went looking for earlier, but I don't think I said anything while I did it. I was curious about the capacitor that I think is over here. I thought it might be a bypass here, but see, there's nothing. So they're providing the bias through this power supply trick, which is quite common in radios. Well, that means that the bottom of this is not at the potential of the chassis. It's a few volts below, from negative to it. And that's why they need to insulate these two. They can't let the cans of these two capacitors touch the chassis. Now, if this is the last one, you can see this one actually goes straight to the chassis. So in this case, you could bolt the can right down to the chassis, job done. The negative connection is made, or the ground connection is made. That's probably what's going on in there. Again, that sort of reinforces the idea that the last guy worked on these, and he may or may not have known the situation. If he knew what he was doing, he figured out the same thing I just figured out. And he made sure to not connect the capacitors to the chassis. That would cause lots of trouble in this radio if you made that mistake, thinking that the chassis is ultimately ground, but in fact, well, you don't want to be getting at. Okay, so we got to be careful where we connect the negatives to these capacitors I'm putting in. And the first one I'm doing again is just this one right here, where the last guy put two in parallel. Okay, let's go back to the radio. Okay, lots of answers there. Remember I said I was going to leave this black wire hanging out? That's why, because I may want to utilize it. So we're going to get this positive lead. See, they indicate the negative here. The negative lead, usually the shorter wire is the negative. I'm going to want to connect to this floating terminal and then to the back to the shell of that capacitor. And the reason for that is a number of connections are made at that point, and I don't want to remake them. Now, son of a gun, one of them is a wire, is one of those yellow cracked up wires. Am I about to change one of those two? Snakes all around in there. Comes all the way to here. So this point is, so look, you know what? So they have here, then there's a resistor off the bottom. So this does have actually another resistor hanging off the bottom. And they showed it on the schematic as a vertical thing and then another resistor coming off, and that's actually physically how it's done, I believe. It goes right down to a two pin connection. Well, we can look at the value of this resistor. So it's a body end dot type. Body is yellow, end is purple. That's 47, and then the dot is not visible, so it's yellow also, unless it's hidden. Body end dot. So you have yellow, purple, yellow. 470K, I believe. Let's peek at the schematic and just see if this adds up. Okay, so right here, no. 225 ohms. 225 ohms. Wow, that doesn't come anywhere near what I just saw. What I just saw, well, you see, this wire goes everywhere. There's a little dot there. I think there's a dot there. Yeah, because they show jumps. No jump, a dot. So is there a 470 ohm resistor connected to this wire lead somewhere? Yeah, probably. Somewhere in this radio. We'll find such a resistor. Not that way. I don't see it. Leaves me wondering a little bit. So where's this? 228. This is a fairly large resistor. Probably a high wattage resistor. This one's 162 ohms. It's also a very small resistor here. Where's this going? Yeah. Hard to see. This is the cathode, so it goes to the cathode here, and then there's two diodes here, but the drawing is hard to look at. One diode's just grounded out, done away with, and the other one is part of the detector. Let's go back down here. Well, we don't know the voltage at this point. Of course, it's a cathode. You don't really want much there. That's interesting. So this is a cathode resistor. This is a cathode resistor for here. And so the grid biasing is achieved by changing the potential of the cathode. So there's nothing going on this wire. There's no bias applied to it. So they've used cathode biasing here. Okay. If it sounds like I know what I'm talking about, great. That's great. Okay, now back to what we're really trying to do, which is stick a capacitor in here and find this 228. It's got to be high wattage, I would think. I don't know. Okay, let's go look for it. Or let's just look in the back of this radio some more. So high wattage resistor right here. It's coming off this connection. So maybe I'm misinterpreting this whole thing still. That's okay. I don't need to get it all straight. I find doing this work is very iterative. You revisit things over and over. Each time you revisit the issue, you figure out a little more because you've got a little more in your bag of tricks at that point. More and more things become clear at first. So not to panic at first if things don't add up. They just have to add up enough for you to make the right decision. And apparently human beings are very, very good at that. Making the right decision when we don't have enough information. So this isn't going to fit right in there, I don't think. I don't think there's enough. I'm going to have to put an extension on it. Or, see, one of the thoughts I had was, well, why use the ground there? I'll just find another local, like closer ground, but no, I can't do that. It has to go back to this key point where I'm going to have big trouble. That's quite a long ways. What would it's probably better to extend the ground side of this. Are you trying to get out? You're trying to escape, are you? No, you got to stay in there for a little longer. Actually, this one doesn't really have to stay in there. I can take it out now. Just leave the wires hanging. Oops. This one also is barfing out some stuff. Let's give them a test. This is also supposed to be a 14. When I was a kid, stripping wires was a real problem. Most kids have trouble when they have to strip their wires. Yeah, I was stripping wires when I was a kid. So lay the wire on my finger like this, then take a knife and go like that over it. So this one reads 25 microfarads, and it's only a 14 on the thing. So again, I think the proper way to interpret this is a leaky capacitor. In this position, a leak in these capacitors, probably not very important, unless it's so bad the capacitor heats up. That's something I thought never happened, even though I'd heard stories. But I finally had a radio just a while ago, and the filter capacitor was overheating, and it took a long time to get going. And as I think I mentioned earlier, there's a thermal runaway situation where one of these things gets hot. Instead of its resistance going up like a resistor, its resistance goes down as it gets hot. And this means there's a potential for something called thermal runaway, where nothing happening, smoke. Just barely makes it in there. So what are these? Because maybe I can replace these and put it straight across here and clean this area up so I can work easier. What are these? So these are added in. It's going, well, let's sort this resistor out now. Now's the time to do it. So we have up at the top here, we have a large capacitor, and we have this 10 watt, this is 10 KT. What's that? 3,500 ohms. We'll see if we can find this. Bridging here, we'll see if we can find what this is supposed to be, because I'm sure this is a replacement. Okay, let's look at that resistor again, right at the end here. Well, what may be the end. So there's a lot of time spent initially just getting familiar with things, and that's what's happening right now. We're investing time to get familiar with things that are going to pay off down the road, even if it's not germane to the situation right now. So we want to look at this resistor, and we want to find another resistor paralleled here. In one of, like, it looks like it would be here or here. So, but it could be anywhere. Oh my gosh, how am I going to do this? Or has he made mistakes? Or is there something wrong with this resistor and he bypassed the defective portion? Yeah, lots of questions there. This is the problem with the radio someone else has worked on, and they've done things contrary to the schematic. So one of these is a 10,000 ohm resistor, and the other one, I'm just looking at it now, just bear with me a second here. 10,000 ohm resistor, and the other one, well, I'm going to replace it, so I'm going to rotate it. Oh, here we are. So one is 8200 7 watt resistor, and the other one is what did I say, 10,000? What did I say? 10,000. So 10,000, that's almost 20,000. That's 18,000 ohms. 18,000 ohms. Look at that. 18,000 ohms. So I'm guessing what happened here is this opened, this is open, and he bypassed it with his own 18,000 ohm resistor combination. That's got to be the explanation of what's in there. That would mean this top piece, well, let's see. On that resistor there are 4 connections. There are 5 terminals, one of them's not used. There are 4 terminals connected. 4 terminals. So 1, 2, 3, and 4. Okay, that's good. So the one at the top is very busy, going every which way, connecting to everything in the radio. The one at the bottom should be going right to the chassis. I gotta find this. This will help know for sure what's going on with this. I gotta find this connection. Okay, let's take a look. Find me that connection. So if it's here, it can't be. There's only 2 wires connected. Oh, wait a minute. One of them goes right back to this capacitor, not quite a ground point. Yeah. Capacitor, not quite a ground point. So let me look again. I gotta look again. I can't keep this in my head properly. Making a lot of video work for myself, flipping back and forth here. So what I saw in there is a connection back to here. Well, that can only come from here. Wait a minute. This is a chassis ground I'm looking for. Okay, so I found a wire that goes back to here. That would mark this point. So again, so this would mean this is part of the, it doesn't add up because of the number of connections. 1, 2, 3, 4, maybe 5 connections. Oh, yeah, one of them's not used, but that shouldn't even appear on the schematic here, or if it did, it would appear as an unconnected terminal, but they didn't put it in. Confusing. I'm going to get the ohm meter out and read some of the resistances in here. I mean, it's all hooked up to the radio, so I don't know what the result would be exactly. But these low resistances, obviously, you can parallel a lot of high resistance against this and still get the same, 225 reading. Now let's do some ohming out here and just see if that doesn't add to the confusion. Well, it probably will. Yeah, you can't be worried about confusion at the start. If you get all frustrated because everything's confusing, well, that's not going to help you. So you just want to keep calm and carry on. So I'm going to put the schematic up here on my own screen. You can't see it. So we're looking for resistances like 3600, 18 across here. Well, let's read across these. If there's 18 in here, then we won't get 18. We'll get 9 or something like that. Okay, here we go. So we're going to get the 18. So almost certainly, if I nip this out, we'll get 0 because the resistor is burned open in here. That's probably what the story is with these. Now, up here, the same rule applies. Well, it's not very high. 3,400 ohms. And we look on the schematic, 3,600. Very good. Okay, so we know where we are finally. So we come down here. That's a long ways. Get on there. There. Oh, that's very slippery. 400. So we're getting 400 ohms. I look on the schematic, 162. And then there's one more, 228. Well, it has to be this thing. I don't believe it. I worked it out to some huge number. But that was based on, I worked it out to 500,000. This is like a 470K. There it is. What's a 470K resistor doing there? He asks wistfully. Oh, I see what it's doing there. Okay, let's jump on the schematic. Okay, so I read this resistor here. Wait a minute. I'll take that back. So we follow this line and we go up to 470 right there. So that's got to be the resistor I'm seeing. So is that resistor, and then 1, 2, 3, and 4. Yeah, 3 I read it was a little high, wasn't it? I can't remember. Short memory. The coffee's wearing off already. So where's this guy? So let's just look at this again. So there should be the 36, which I found, the 18, which is installed as a bypass, 162 and 228. 162 and 228. I wonder if this is a slightly different version of the radio that we have in front of us. 162, 228. Where are you? Okay, back to the radio. 162, 228. $400. 160 on an unused terminal. $228. So it looks like they put in a resistor to match the schematic, but then when they wired the radio, they did something a little different. Right in the factory, because this has never had a connection to it. Or this whole resistor's been replaced. Now, it's not easy. This is riveted in. This is a rivet. So no, so this has not been replaced. So I think this says the schematic I got is slightly different than what the radio itself is. That's not helping much. That doesn't help. That's a bit of a paralyzing effect. Well, we can bridge this with a better choice in resistors. So we can neaten that up and get this out of the way. We should check this one here, 3500. Well, I got the ohm meter out. Oh, I did this already, didn't I? Wait a minute. Wait a minute. Well, this is across here. Is this also burned out? Is this whole resistor burned up? How can that happen? Okay, so we read it, we get this value, 3500. Slightly reduced. Not much. 3400 on the meter. Sorry, move the meter. So I think what we're finding here is that this resistor got smoked. Oh my gosh, wait a minute. Oh, okay, this is where it's time to stop and think hard before making a mistake. See, my computer just rang the bell there. Jim, you're right on the money. Better stop for a minute and think about this. You know, an alternative to doing this back in the day would be to replace this resistor. A lot of radios have one of these in it, but they're all different. They're all specific to the resistor, to the radio they're in. So how do you get one of these today? You'd have to get one of these. If you get this whole radio, well, what are you going to do? You're going to swap the resistor over? Just destroy one whole radio to have another? It stops making sense. So, what you start doing is this kind of stuff. But it doesn't make sense to me that this would be... Well, wait, if you burn it open here... Is it... No, you could still use the rest of it. You'd have to burn it open here and burn it open in here, too. So one way to deal with this would be to remove all these connections and then test the resistor directly. That's ridiculous. That's too much work. That's out of the question. With a 3500 here and a reading of 3500 from here to here, and this is supposed to be 3200, it's virtually guaranteed that's what's happened. Somehow this burned open, somehow burned open down here too. That's a bad thing. What happened in this radio that burned these guys out? You need a short somewhere in the radio, a critical short, pulling heavy current through both of these. Now it's like a chain, you know. If you have a chain with 10 links and you pull on it hard enough, the chain will break. But guess what? It only breaks one link. It doesn't break two links. You can't pull the chain and break two links. Same thing here. It would have to be something like one part burned open, and then that set up the situation for the other part to be overheated. And that kind of thing would generate a lot of smoke in that, I think. I don't see any evidence that this ever was hot. Conflicting observations. Well, we can remove. I plan on replacing these two, so I can cut them off, and then we can test directly through there. Well, let's do that. Should I first check and make sure I have a? Was it 18? I better check and make sure I have a replacement resistor before I make a foolish move here. And you know what? A little more coffee might help. So I'm kind of in the same boat as the last guy, trying to find a suitable resistor. You can see I've been going through my resistors here, trying to pick one that's exactly, I think it's 18.7, I think is what the schematic's calling for here. Yeah, 18.7K. So, but what are the values of the ones that are in there right now? I ask very curiously. So let's measure that. This is what's in there right now. Now it's in the circuit, so you can see there's a capacitor involved somehow. Well, it's not going to make it to 15 even, I don't think. So there's not even 15 in here right now. It's supposed to be almost 19. Almost 19. So almost 19, I've got a 20, but this actually measures a little low. Let's measure it again. How accurate do these have to be? Well, it's based on how accurate is this one. So see, that's measuring in at 19. That's pretty close. 19. 18.7. Wow, that's really close. So this is probably going to be the winner. I also have this guy, which I think was 22. Ooh, 27. Yeah, 27 is too high. And all the rest of these are quite low. Interestingly enough, in my tray, I have one of these bolted to the side of your radio. But this is of no value in this case. Okay. I suspect I've got a bunch more of these resistors somewhere. But I think this guy's going to be the winner right here. So he can fit in there really nicely. It's a 5-watt resistor. And this can get pretty hot and still be fine. So I think that's what I'm going to do. I'm going to put this guy in, take these guys out. Wow. Yeah, it takes a long time to make a decision here, but you don't want to make a mistake. This is the fundamental part of the power supply. Mess this up. So what we're going to find out is I'm going to nip this here, is this really open circuit in here? Maybe it's just gone really high or something. Here we go. So, you know, there is a wire connected here. We'd have to study the schematic a long time, figure out what's happening here, why we're getting this reading. We're not just getting a zero, because I'm sure stuff is flowing around through the radio in various ways to get here. It could be quite complicated actually to justify that reading. Just went above the rating of the setting there, so it's around 60K. But can there be any doubt this is the right thing to do? Sure. Sure. Let's give it a little bit of standoff wire here too. The heat that builds up in here can travel down the wires and get into whatever the wire is connected to. So you kind of often want to leave a little bit of extra wire here so the heat has trouble getting down there. Like this one's done. There's just a bit of wire here. It's not right up tight. Okay, I'm going to install that. I will install that. Okay, got that guy in. Now, lots of space now to work on this. Negative guy goes down. How much play is in here? Well, this is on one of those cracked wires, so if I push this, crack, 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 and maybe a short circuit. So just a little short. You have to put an extension wire on it. Okay, we will do that. The advantage of doing that is I could do it in a way that it's all insulated wire then. And it's a little bit better. Good, I'll get that done. That's what that looks like now. I've extended the positive side. Okay. Okay, so I was pulling out these old black wires, leftovers from the capacitors I removed. I was just tugging on the black wire, and it popped right off. So this was cold soldered down onto this terminal, because look at the size of that terminal. That's a tough one to heat up, and I could see the solder didn't look like it had flowed on. It looked like it was pasted on. So there you go. Cold joint. Probably had no negative bearing on the radio, but a close call, really. Okay, so where'd my capacitor go? So I'm putting them in here. Now there's a nice little tidbit of wire sticking up here. Fantastic. Because I don't want to try to melt that big blob of solder myself. Okay, so I'll put the capacitor in. Get him in. We can try the radio then. Okay, now I've got the other capacitor to put in here. Got the one I've put in here. Got to put the other one I took out, which goes to this red wire, which is still connected to the original capacitor. So I'm going to reach up under here. I'm going to just break the connection to the original capacitor, because that's probably not a good thing to keep there. Clearance there, and all these wires are going to break there. There we go. Don't want to move things too far. Now this little 10 microfarad capacitor goes right in. Perfect. Okay, we'll get this guy installed. Then we can operate the radio. See if it still works. Okay, just about ready to try out the radio now and make sure it still works. So working right on the power supply. The mistake here is bad news. It's bad news. Just double checking to make sure I have the negatives hooked up to the negative side of things. And I do. Positive here. And now these cracked wires are shorting out as far as I can see. Okay, let's tip it down. Okay, speaker's still plugged in. Here. So we're going to go through the dim bulbs for sure, because maybe I messed things up. I do from time to time. So the set is switched on, but the power's not here yet. And I can't remember which one was the volume control. So here we go. Through the lights. Oh, it just barely lit up. Ooh, what's that mean? I thought it was going to come on bright and then go down. Ooh, ooh, ooh. What does that mean? Does that mean something? Well, they're not on full bright. If they're on full bright, short circuit, bad news, run away. But you can see that's not happened. The panel lights have come on. Give it a little bit of time because it's got 85 volts pushing on it right now. Oh, I was going to try to clean this. Yeah, the unknown control. No antenna, Jim. No antenna. Okay, so volume's down, or whatever they are again. And well, that's a good sign. Tone, Jim. Tone. Very distinctly tone. Volume. That's with all of 85 volts. That's 85 volts, and that's also picking up AM on a outdoor wire antenna. Set works. Fantastic. So what we did is we removed the last two of these from the circuit entirely. I'm sorry, one of these we removed. The other one was already removed. The third one we'll work on when we get there. So power supply seems secure now. Don't know what output voltage is coming from it because of those resistors. It could be a little different. I don't know yet if those resistors are going to, the ones I put in is going to burn up. Not very likely, but we'll look into that as we go. That's it for today. Very good. Much more familiarity with the radio, and feeling good. Feeling good. Thanks a lot for watching, and see you on the next video. Bye.